Deriving the equation of a line using determinants. Hello everyone. Welcome to today's lesson. Before we dive into our new topic, let's take a moment to reflect on what we've already learned. In our previous subsection, we established a very important geometric principle, that if 3 points are collinear, meaning they all lie on the exact same straight line, then the area of the triangle formed by those 3 points is exactly 0. Now, in this session, we are going to take that geometric property and use it as a powerful tool. We will leverage the idea of zero area to derive the algebraic equation of a straight line that passes through 2 specific, given points. By the end of this lesson, you'll see how determinants can simplify this entire process. The conceptual logic. Think about what a straight line actually is. It is essentially a collection of infinitely many points that all lie on the same path, meaning they are all collinear. Now suppose we are given 2 fixed points, which we can call A with coordinates x1, y1, and B with coordinates x2, y2. If we want to find the equation for the line passing through them, we need to describe any other arbitrary point, let's call it P, with coordinates x and y. This point P will lie on our line if, and only if, the 3 points, A, B, and P, are all collinear. As we mentioned at the start of this lesson, if these 3 points are collinear, the area of the triangle they would form is exactly 0. This is the key. Because of this, we can use the determinant formula for the area of a triangle to set up an equation. By solving this, we will be able to find the specific mathematical relationship between x and y, which ultimately gives us the equation of the line. In the next few slides, I will show you exactly how to set up and expand this determinant step by step. Now that we've established the connection between collinearity and a zero area in the previous slide, let's look at the conceptual logic behind our method. Step-by-step derivation process. Now that we understand the underlying logic, that any point on our line must form a triangle with zero area alongside our 2 fixed points, let's break down the actual derivation into a clear, step-by-step process. To find the equation of a line passing through the point x sub 1, y sub 1, and the point x sub 2, y sub 2, we are going to follow a structured approach. The very first step is to define the points. First, we must clearly identify our 2 known fixed points, which we'll label as x sub 1, y sub her, and x sub 2, y sub 2. But to move from just having 2 points to having a full equation, we need to introduce a third general point, which we'll call P, with coordinates x and y. This point, P, represents any arbitrary point that could potentially lie anywhere on that infinite straight line. By treating x and y as variables, we are setting the stage to find the mathematical relationship that connects them, which we will expand upon in the next steps using our determinant formula. Step-by-step derivation process, continued. In step 2, we are going to set up our area determinant. We take those 3 points we just defined, the general point with x and y, and our 2 known points with their respective subscripts, and we place them into the determinant formula used for the area of a triangle. You'll see the formula on the screen, where the area equals 1/2, multiplied by a 3×3 determinant. The first row contains our variables x, y, and the number 1. The second row contains x sub 1, y sub 1, and 1. And the third row contains x sub 2, y sub 2, and 1. Moving to step 3, we apply the condition of collinearity. Remember from our earlier discussion that if points lie on the same straight line, they don't form a triangle at all, the area is simply 0. Because of this, we set our entire determinant expression equal to 0. Now, a quick tip. You'll notice the 1/2 multiplier in the formula. Since we are setting the entire expression to 0, that 1/2 doesn't actually change anything, because 1/2 times 0 is still 0. So for our calculations, we can simply ignore that constant and focus on setting the determinant itself equal to 0. This leaves us with our determinant of x, y, and 1, through x sub 1, y sub 1, and 1, through x sub 2, y sub 2, and 1, all equal to 0. Now that we have identified our 2 fixed points and our general point, P, let's move on to the actual setup. Step-by-step derivation process, continued. In step 4, we need to expand the determinant. We'll do this by expanding along the first row, which is the row containing our unknown variables, x and y. To do this, we take each element in that first row and multiply it by its corresponding minor. First, we take x and multiply it by the determinant of the remaining 2 by 2 matrix, which gives us x times the quantity y sub 1 times 1 minus y sub 2 times 1. Next, remember the sign pattern for determinants. We must subtract the second term. So, we take y and multiply it by the determinant of the remaining elements, resulting in negative y times the quantity x sub 1 times 1 minus x sub 2 times 1. Finally, we take our third element, which is just the constant one, and multiply it by the determinant of the remaining 2 by 2 matrix, which is 1 times the quantity x sub 1 times y sub 2 minus x sub 2 times y sub 1. We set this entire expanded expression equal to 0. This brings us to step 5, where our goal is to simplify. Once you perform all that multiplication and combine the like terms, you will notice that the expression settles into a much cleaner, standard linear form. A times x plus b times y plus c equals 0. This is the general form of a straight line, where a b and c are just constant numbers. Now that we have set our determinant equal to 0, we move into the algebraic heavy lifting. In the next slide, we're going to see this exact process in action using a real-world engineering example to make it much more concrete. Practical example. Now that we have understood the theoretical derivation and the steps involved, let's put this into practice with a real-world application. Imagine you are a civil engineer tasked with mapping out a straight road that connects two specific survey markers. These markers are located at the coordinates 2, 3, and 4, 7. To ensure the road stays perfectly straight, and to check if any other landmarks or structures fall along the same path, you need to find the linear equation that represents this road. So, our specific goal here is to find the equation of the line that passes through the points 2, 3, and 4, 7. To solve this, we will follow the same systematic approach we just discussed. In step 1, we need to identify our points. We will take our two known points, where x sub 1, y sub 1 equals 2, 3, and x sub 2, y sub r 2 equals 4, 7. Finally, we introduce our general point, which is x, y, representing any arbitrary point along this road. We will use these values in the determinant setup in the next slide. Practical example, continued. Step 2, we are going to set up our determinant for collinearity. Remember, our goal is to ensure the area of the triangle formed by our two known points and our general point, x and y, is exactly 0. To do this, we arrange our coordinates into a 3 by 3 matrix. In the first row, we place our unknown variables, x, y, and the number 1. In the second row, we plug in the coordinates from our first point, which are 2, 3, and 1. Finally, in the third row, we use our second point, 4, 7, and 1. We then set this entire determinant equal to 0. Moving on to step 3, we need to expand this determinant along the first row. This is where we break the large matrix down into smaller, more manageable 2 by 2 determinants. We take our first element, x, and multiply it by the determinant of the 2 by 2 matrix that remains when we ignore the first row and first column. That's 3, 1, 7, and 1. Next, we take our second element, y, and subtract the determinant of the 2 by 2 matrix formed by the remaining elements, which are 2, 1, 4, and 1. Lastly, we take our third element, the number 1, and multiply it by the determinant of the remaining 2 by 2 matrix containing 2, 3, 4, and 7. Don't forget that middle minus sign. It's crucial for the correct expansion. Finally, in step 4, let's actually calculate those smaller 2 by 2 determinants to simplify the expression. For the x term, we multiply 3 by 1 and subtract 7 by 1. For the y term, we multiply 2 by 1 and subtract 4 by 1. And for our constant term, we multiply 2 by 7 and subtract 4 by 3. When we perform these subtractions, we get x times the quantity 3 minus 7, minus y times the quantity 2 minus 4, plus 1 times the quantity 14 minus 12, all set equal to 0. We are now just a few simple arithmetic steps away from our final linear equation. Now that we have identified our two fixed points from the previous slide, let's move into the actual calculation. Practical example continued. Now that we have expanded the determinant and calculated all our minor determinants in the previous step, we move to step 5, which is to simplify our equation into its final, cleanest form. Looking at our expression, we have negative 4x minus y multiplied by negative 2 plus 2 all equal to 0. When we perform the multiplication for the y term, remembering that a negative times a negative becomes a positive, the equation becomes negative 4x plus 2y plus 2 equals 0. While this is a valid linear equation, in mathematics, we always aim for the simplest version. To make this easier to work with, let's divide the entire equation by negative 2. Dividing negative 4x by negative 2 gives us 2x, dividing positive 2y by negative 2 gives us negative y, and dividing positive 2 by negative 2 leaves us with negative 1. So, our final simplified equation of the line is 2x minus y minus 1 equals 0. This result gives us the precise mathematical path for that road the engineer was trying to map. In the next slide, we will wrap up this lesson by reviewing the key takeaways and some common pitfalls to avoid. Key takeaways. First, let's revisit the core geometric principle we used. Collinearity implies a zero area. This is the fundamental link that makes this entire method work. Remember, we started with the idea that if 3 points lie on the same straight line, they cannot form a triangle with any height or width, meaning the area of the triangle they form must be exactly 0. Second, notice the importance of the general point. In our derivation, we didn't just use 3 fixed numbers. We introduced a general point, x, y, as one of our vertices. By doing this, we aren't just calculating a single numerical value or a static area. Instead, we are creating a functional relationship, an algebraic equation, that describes every single point that belongs to that line. Finally, think of the determinant as a powerful mathematical tool. While you might be used to the traditional method of finding the slope, m, and then using the point-slope formula, using determinants provides a much more structured and organized way to handle coordinates. It allows you to plug your values directly into a matrix format, which can be much cleaner and less prone to error when dealing with complex coordinates. All right, we have successfully worked through our example, and now we have reached our summary slide. Before we move on to discuss some common pitfalls to avoid in your exams, let's recap the key takeaways from today's lesson. Now, let's take a moment to look at some common mistakes that students often make when applying this method. Common mistakes. First, keep a close eye on your determinant setup. A very common mistake is ignoring that third column. When you are setting up your matrix, you must include that column of ones. Without those ones, the determinant loses its geometric meaning and will no longer correctly represent the area of a triangle in a two-dimensional plane. Second, be extremely careful with your signs during the expansion process. As we saw in our step-by-step derivation, when you expand along the first row, the middle term, the term containing y, must be subtracted. Remember the pattern. A sub 1 times the cofactor minus a sub 1 2 times the cofactor plus a sub 1 3 times the cofactor. If you forget to flip the sign on that second term, your entire linear equation will be incorrect. Finally, don't get hung up on the 1/2 fraction from the area formula. I've seen many students spend extra time trying to multiply their final result by 1/2. However, as we established earlier in the lesson, since we are working with the condition of collinearity, the area is exactly 0. And since 1/2 times 0 is still 0, that constant factor doesn't actually change our final equation. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even if you understand the logic we've discussed, it is very easy to make small computational errors that can lead to the wrong equation. Keep these 3 points in mind, and you'll be well on your way to mastering this method.